Welcome back to ECE 442-542. Homework number 2 is due tomorrow at a little bit before midnight. And if you're submitting your homework assignment at that point, you might try to make sure that you put it into one document, if at all possible, and maybe a PDF or a Word file. The grader had over maybe 150 documents to try to open up and examine and grade, so we're trying to converge to a easier format for the grader. So just take note of that if you're submitting homework number 2 via the Dropbox. The review session, the voting finished, and the consensus, well, not the consensus, but a larger percentage voted for Monday at 7 p.m. So we'll try to do that immediately following class on Monday. We'll go until I'm finished, so we'll finish at 7:05. Starting at 7. All right, maybe that wasn't funny, but we'll try to do some bit of review. There is material on exam number 1 from previous semesters, but you might pay attention to which particular problems. You may not be responsible for all of the problems on all of those practice exams. In previous semesters, when this class was taught, the assumption was the students had already taken the earlier analog controls class. That was a prerequisite. That's no longer the case. So you may see some material on exam number 1 that you may not be held responsible for this exam number 1, but you may have to deal with that for future exams this semester. So if you see that and you go, well, I don't even know where that's coming from, stay tuned. We may or may not approach it that way. I did provide a little bit more Laplace material on D2L, and you can find that in the prerequisites review section on the contents tab of the D2L website, and that was to maybe address the sinusoidal steady state or the graphical analysis or the graphical way of finding the frequency response behavior given a transfer function h of s. So if you want some review on that, that's available on the website under, I think, Laplace material applications. Exam number 1, I hope this comes as no surprise, that's in a week. So a week from today is exam number 1. And we'll talk more about that maybe on Monday as far as the process, but it's basically a sheet of notes will be allowed, 8.5 by 11 inches. Don't get to use your own units of measure, but and that's usually front and back. I'm not going to police if you just have one side of that 8.5 by 11. You'll have both sides of that available. Today, the goal is to discuss the region of convergence. And in particular, we need this understanding if we want to go both directions with the Z transform. We've now learned how to calculate or derive a Z transform. If we want to go the other way, we need to know what the region of convergence allows us in terms of additional information. That's what I want to cover today. So let's look at the region of convergence, and here's how I will motivate that. Suppose somebody provides you with, or if someone gives you a transform, capital X of Z equaling Z over Z minus 1/2. What can you tell me, or what can you tell them about the time domain waveform little x of n? Or what can be said about x of n, the inverse z transform of capital X of z? So they now given you this capital X of z, and you maybe have this transform table in hand, and now you are asked, what is little x of n? Can you give me that information, or the person asking that question? So it's a loaded question, maybe, and if it's loaded, you always answer, it depends, right? Or you could say, you really need more information. And the additional information is you need to know what's the region of convergence. You need two pieces of information in order to go backwards from a z transform. You need the transform, and you need to know the region of convergence. With those two pieces, then you can be better informed to explain or describe what the time domain waveform x of n equals. Now, why did we not need to worry about that for Laplace? Most of our Laplace discussion has always been one-sided, meaning we were always dealing with time domain waveforms for non-negative values of time t. Then we could immediately inverse Laplace transform and obtain this x of t expression. So let's look at this issue based on this concept of needing more than just the transform to get back the time domain waveform little x of n. If I simply give you a generic capital X of z, which I did in that earlier question, then little x of n could be a right-sided sequence, and we'll see maybe that that's more restrictive than just a right-sided sequence. But by a right-sided sequence, what I'm meaning is that we have something that just keeps going in the right half of the time axis. Here's our time in, and this is now x of n. So that's a right, and it was 0 over here leading up to that. So it's only on the right side, or it continues in the right half of the time domain. Or, so if you're just given capital X of z, you don't know if it's causal, if it was just non-negative, or anti-causal or non-causal on the left. And so I'll say, or little x of n could be a left-sided sequence. Meaning now this sequence to be left-sided, that just means that it's always on for negative values of time, and it stops, or it doesn't have a right side to it. And the region, or the type of signal, left-sided, right-sided, or anti-causal, causal, the type of signal that you have, or if you have a two-sided sequence, whatever sequence you have depends on the region of convergence. The waveform type for x of n depends on the region, let me say in the complex plane, and I'll be specific in the complex z plane, where that z transform actually converged, or where that z transform converges, or where that sum is bounded, or when it exists. And that's what we call the region of convergence. Let's look at some examples that give rise to different regions of convergence, but yet they have consistent looking capital X of z's, or similar looking capital X of z's. That's what we just sort of motivated this whole discussion with. Suppose you're given x sub 1 of n that's 1/2 to the n, but that's true for negative values of the time index n. And now we can compute what some of those are just to get an idea. Now we are evaluating that for, so I need to make sure my subscript is clear. Whoops. I'm not doing it with the time on the subscript. I'll do that in the argument. So x sub 1 at time step n equal to -1 is now 1/2 to the -1, or 1 over 1/2, which is 2. X sub 1 to the -2 is 1/2 to the -2, which is 1 over 1/2 squared, or 4. So it's 2, 4, 8, 16 as we're going back in the negative time direction, and we could sketch that. Here's little n. Here's x sub 1 of n. And we just said that for -1, -2, we computed. This was 2, this was 4, this was 8, and it just keeps going. We didn't say anything about whether that time domain waveform was stable or bounded. This one's obviously going unbounded, isn't it? But we can find a z transform for that unbounded sequence of time. Let's find that. But this is what it looks like. We have 1/2, something smaller than 1, for negative time indices. And that's going to go unbounded as we go more negative in time. Let's compute its z transform. And now we're approaching the exam, so you go, oh, I'm looking for partial credit. So I know the definition of the z transform. I'll write that down. Okay, now you get 1/2 point out of 25 points for writing that. Well, you got partial credit, right? So there's capital X sub 1 of z. By definition, that's what it is, but you should be able to get even more, because we said, oh, that's only non-zero, this x sub 1 of n, for negative values of the index of time. So we know we're going from -infinity only up to -1. We're not going to 0 for a little n, or 2, or 5. We're done after we hit -1. And this, we know its functional form. It was 1/2 to the n. That was x sub 1 of n. And that's scaled by z to the -n. Well, we could make this a little bit cleaner just by realizing that 1/2 is 2 to the -1, and now we can combine those two and raise them to a -n power, meaning now we can say capital X sub 1 of z, or the z transform of little x sub 1 of n, is now this sum from n equal -infinity to -1 of 2z to the minus n. But this is not what we were doing before. We didn't have negative indices with this guy. So I want to make this look something that I feel more comfortable with. And I can do that by simply changing the variable, not the variable of integration, but the variable of the sum. So let me go ahead and let L equal minus n. Now if I do that, that cleans this up or makes it look a little bit more familiar. Now L is going to go from 1, so I'm going to just reorder my limits. L now goes from minus 1, which L is now 1, up to infinity. I still have this 2z, but now my minus n becomes L. And this looks like what I'm used to seeing. This sum over positive indices with something, this quantity, raised to a positive exponent. And when do I know this converges? In this particular example, what do I know has to happen to this quantity raised to the L? That needs to be less than 1, doesn't it? So now I know that this is going to converge as long as that quantity's magnitude, 2z, is less than 1. So I'm trying to find its z transform. But that just means that I need z, the magnitude of z, to be less than this 1/2. And that's my region of convergence. Now I have to figure out what that looks like. But to do that, maybe I say, you know what? I'm just going to make that W so I don't have to keep writing 2z. To z or not to z. I'm sorry. That's what you say about halfway through this lecture, right? To z or not to z. Not Shakespeare, huh? I could bottle that and sell it. Sleep aids, right? Never mind. Somebody probably, I already have the patent on that. So here's x sub 1 of z is now W, that's the first L, that's L equal 1, plus W squared, etc., all the way up to W to infinite power. And we know how to play with this, except now I'm going to try a little different tact. I'm actually going to multiply this by the inverse of W, just to be different. So let me now say this is now scaled by W to the minus 1. That now gives me 1 plus W squared, etc. But I can still compare those two infinitely long sums. And I can now say, oh, that's 1 minus W inverse x sub 1 of z. And what do I have on the right-hand side? I now have minus 1, don't I? So that now, capital X sub 1 of z is going to be this minus 1, 1 minus the inverse of W. Or, if I multiply through by W over W, or 1, that's okay. I can always multiply by 1. I now have minus W over W minus 1, but W wasn't what I started with. That was just a made-up variable to make my algebra easier or my hand to not cramp as quickly. So now I have x sub 1 of z is equal to what W was, which was 2z. Oh yeah, we shouldn't forget what that was 2z. We have 2z over 2z minus 1. And if we multiplied everything by 1/2 or factor down a 2 in the denominator, we would end up with minus z over z minus 1/2. And where was that valid, or for what values of z did this sum converge? That we have to go back to the region of convergence and we say, oh, z's magnitude needs to be less than 1/2. And this should look like it's related to what we started with before, that z over z minus 1/2. And we found this one from a left-sided sequence. This was an anti-causal waveform to begin with, and now we came up with this as a z transform. It's valid as far as a region of convergence. Where's the pole of this transform located? It's at positive 1/2, isn't it? It's right here. Here is our z-plane. Where is our region of convergence? So here is our pole. Now you'll have to just sort of believe me and assume that's a perfect disk of radius 1/2. This is our region of convergence right there for this problem. This sequence, this time domain sequence that was left-sided, it was going unbounded, has a region of convergence that's interior to or inside the pole of that transform. And that has some significance. Let's look at some observations. One is that the time domain response was unbounded. Or maybe you like to refer to that as an unstable waveform. Yes? The region of convergence is disconnected from stability. So that's what I'm hoping to draw from this. So we don't need to connect region of convergence. Well, we can in just a minute, but the time sequence, we can have an unstable time sequence and still have a transform, okay? Now, what we've said, this we knew from the beginning when somebody gave us 1/2 to the n, where n was a negative time index. That was given, so we knew that our time domain response was unbounded. But what we can look at here is, where is this region of convergence relative to the unit circle? Here's the unit circle. Is that unit circle contained inside the region of convergence? Does it lie inside the, by inside I mean the region of convergence would need to shade and cover up that unit circle. So that's an observation we can make. The region of convergence does not contain the unit circle. And this is a connection that you can make, is because that unit circle is not contained within the region of convergence, you know that your time domain waveform is unstable. Another observation that we can make, or maybe just restate that last one, is that the region of convergence, let's see how I want to word this so that it's clear, is interior. Well, this is actually a separate issue. The region of convergence is interior to all poles. We only had one pole in this case, but that actually means that we had a left-sided sequence or an anti-causal time domain waveform. The region of convergence is interior to all poles, then a left-sided sequence. Or that says that x of n is not equal to 0 for negative time indices. And that's when we have our region of convergence interior to all poles. And we'll maybe show that in a minute as far as where that's coming from. But now let's just make that observation. We have a left-sided sequence, and the region of convergence is interior to all the poles. Let's look at another time domain waveform so that we can compare it to this one. Suppose now that we have x sub 2 of n is 1/2 to the n, but now let's make that a right-sided sequence, n greater than or equal to 0. So that now we're going to start at 1. At 1 we'll be at 1/2. At 2 we'll be half of that, 3, etc. And that just is this exponential decay. That's now this different, but it started 1/2 to the n. But now I'm telling you when it's defined to be 1/2 to the n for non-negative values of n. We can now find its z-transform. Capital X sub 2 of z is now this sum from n equal minus infinity to infinity. You're trying to get 1 point on the exam, so you're going to get your other half point for this. X of 2 z to the minus n. You have to not be zing in order to catch these jokes, right? Now what do I do? You want more than half a point. What's little n? Now we can remove the negative indices on n. We have 1/2 to the n z to the minus n. Or this is now from n equals 0 to infinity of 1/2z to the n. And when does this converge? We want that value, 1/2z, that argument that's raised to the power of n, we need that to have a magnitude less than 1. So we need 1/2z less than 1. Or, if we pull the z out, we need 1/2, or to be less than the magnitude of z, or we need z to go outside of 1/2. Again, if we call this term, just to make my writing easier, if we call that w of sub 2, then we know that capital X sub 2 of z is equal to 1/1 minus w2, using our technique for finding that sum. But that's just 1/1 minus 1/2z. If I multiply everything by z over z, or 1, I end up with z over z minus 1/2. And when is that true? That's true as long as the magnitude of z is beyond a disk of radius 1/2. Meaning this where's my pole in this transform? And this transform looks, I hope, very similar to this one, right? Z over z minus 1/2. This one's a negative, but the other one was just z over z minus 1/2. But where is the pole in this transform? 1/2 again. But now where's my region of convergence? It's outside this. That's supposed to be a circle. Man. The region of convergence is here. And where is that relative to the unit circle? Or where's the unit circle relative to this region of convergence? There's the unit circle, and it lies within the region of convergence. I've now colored the region of convergence, and in so coloring, I've now colored up my unit circle, or the unit circle is contained within the region of convergence. Is that clear on the terminology or the way I'm describing that? We can now make some observations for this waveform. The time domain sequence which was x, little x sub 2 of n, this one was bounded, wasn't it? It was collapsing with time, or it was stable. And what did we know about the region of convergence and the unit circle? The region of convergence contains the unit circle. Again, that's the connection that we can make. Because that unit circle was within or contained within the region of convergence, we know the time domain sequence had to converge, or was bounded. That's what I should say, or was a stable sequence. The other point that we can make is that the region of convergence is exterior to all the poles. In this case, we only have one pole, but that's all of the poles, and that actually corresponded to a right-sided sequence, or a causal sequence. The point of all of this, these last two examples, was to try to convince you that if you're given a Z transform, and in this case we were given a particular one, Z over Z minus 1/2, what that corresponds to in the time domain depends on the region of convergence. In one of the cases, when we had a left-sided sequence, the region of convergence was interior to all the poles. When we had a right-sided sequence, the region of convergence was exterior to all of the poles. And that's the connection. Let's look at another situation. Let's step it up a little bit and look at what could possibly happen if we have two poles instead of just one. So let's look at different possibilities for the region of convergence when we have two poles. Now, what we can take away just from this picture is the region of convergence did not contain that pole, did it? It was just beyond that pole. Likewise up here, the region of convergence, by definition of that region of convergence, in order to allow that to collapse down, that pole had to not be inside the region of convergence. So no matter what we have, all of our poles will never have any of the poles in our region of convergence. So that's something I want to point out right now when we're talking about these two different pole cases. Note, the region of convergence never contains any poles. And I hope that's clear. If you have poles, none of them can be inside the units or inside the region of convergence. Let's look at some possibilities with two poles. Suppose that now somebody says, okay, I have a pole at 1/2 and 3/4. And let's say that the region of convergence is exterior to the largest pole. Somebody's been sitting on my circle, but that's supposed to be 3/4 all the way around. And now we're saying this is the region of convergence. We'll show this in a little bit, but what does that mean? The last conclusion, when we had our region of convergence exterior to all of our poles, what did that correspond to in terms of the type of the sequence, the time domain sequence? Was it causal or anti-causal? Now we're not talking stability, because stability is divorced from this. It could be unstable or stable. That we'll have to look at later. But now what I want to say is that if the region of convergence is exterior to all of our poles, then we know that the time domain sequence, x of n, is causal. So x of n is equal to 0 for all negative values of n. Now, if we look at the other case, which we looked at in the first example, suppose now we still have those same poles, which were at 1/2, is that right? Yeah, and 3/4. And suppose that now the region of convergence is there. Or the region of convergence is interior, maybe I should say to the smallest. Why don't I say that? Region of convergence is interior to the smallest, I'm meaning the pole with the smallest radius. The region of convergence is interior to the smallest pole. then we know that this time domain sequence, x of n, is anti-causal, or x of n is equal to 0 for all non-negative values of n. So those are two cases where we have one-sided sequences where the poles are both either interior to or exterior to the region of convergence. But with two poles, we could have something a little bit more interesting. And probably only I would think of it this way, but maybe not. Whoops. Say we have a pole at 1/2 and a pole at 3/4. And the region of convergence cannot contain any pole. So we've had the case where it was interior, the region of convergence. We had the case where the region of convergence was exterior. I'm hungry. Did I see a donut or a bagel earlier? So if we have a donut shape, where's the region of convergence? If these poles cannot be, you'll have to believe my drawing. Now the region of convergence is between those. It's greater than 1/2 and less than 3/4. It can't be greater than 1/2, can it? It can't be interior to 3/4, but it can be that intersection and still not contain any of those poles. So in this case, the region of convergence is in between sets of poles. Or the region of convergence is annular, or a donut. That means that now one of those, if we look at these now in isolation, where's the region of convergence relative to 3/4? It's interior, right? So when the region of convergence was interior to a pole, what was the sided sequence that corresponded to? That was anti-causal, wasn't it? So now if we had 3/4 as our mode, it would be raised to the negative indices in time. 1/2 is interior, or the region of convergence is exterior to 1/2. It would now be 1/2 to the n, where n corresponded to the positive time indices. So now we have both positive and negative time indices, or we now have a two-sided sequence in little x of n. So with this region of convergence in between, or annular, little x of n is a two-sided sequence. So let's see if we can actually sort of convince ourselves of why that is, and it's all going to boil down to the definition of the z-transform. Let's look at an example, and during the process of this example, hopefully we'll make it clear how these different interior and exterior characteristics of the region of convergence relative to the poles correspond to the appropriate sided time domain waveform, whether it's left-sided or right-sided, or whether it's anti-causal or causal. Here's the example. Suppose we now want to find f of n if its z-transform, capital F of z, is z over z minus 1/2 z minus 3/4, and we're told that z, and now I'm going to mess you up, but that's bigger than 3/4. You usually saying 3/4 is less than z, but z is greater than 3/4. This is now our region of convergence. Pictorially then, that's the picture that we have. Here's the region of convergence, and this is our z-plane with the poles indicated. We have a 0, but I'm not even going to indicate where that is. That's right at the origin. We don't worry about that. We just worry about poles, so I'm not going to indicate that. But if we look at this in terms of the general equation or expression for the z-transform, we know the z-transform looks like that by definition. Now, if we write that out, or a few terms, we're coming in from negative time indices, so we have f of minus 2, z to the minus 2, so that's z squared, right? F at time minus 2 is scaled by z to the minus that time index minus 2. So we have z to the minus 2, or z squared. We have f of minus 1, z to the minus 1, or z to the 1, plus f of 0, z to the 0, plus f of 1, z to the minus 1, plus f of 2, z to the minus 2, plus dot, dot, dot. But what do we know we can discern about this expression or these particular time domain values if we interpret information from the region of convergence? If we look out here at the region of convergence, now I can walk really, really well. I could just keep walking, couldn't I? What value of z is still in that region of convergence? Pardon? How big of a value of z is still in our region of convergence? Or how big is that region of convergence in extent? It's infinite, isn't it? That region of convergence includes an infinite value of z. So let's see if that tells us anything about what some of these values have to be. Does that force something, some condition to be true? From the region of convergence, we can see that that includes unbounded values of this complex variable z, that is, z is marching off to infinity. If z is marching off to infinity, what do we know if this was included in our sum and our sum was converging? What do we know has to happen to f of minus 1 if it's getting scaled by an infinite value? It has to be 0, doesn't it? F of minus 2 is getting scaled by an infinite value squared. That has to be forced to 0. All of these waveform values in time with negative indices have to be 0 if this region of convergence corresponds to this transform. Because the transform exists, and now we can conclude that all of these negative time index pieces to the little f of n, or the time sequence, have to vanish. They have to be 0. So this now says that f of n is equal to 0 for all negative values of n. So we don't have the left side. We have a right-sided sequence starting at n equals 0 and going on, and that's a causal sequence, isn't it? So the fact that we have this unbounded value of z in our region of convergence, we can now conclude that our time domain waveform can only exist for positive values of n. Is that okay? Now that we know that, now we know we have a one-sided sequence, and we can use that to help us figure out how to raise these modes to a particular power. We now know the power that we'll raise these modes to is positive in the time index. Now, here's a slightly modified strategy to maybe what you're used to for the Laplace partial fraction expansion. If you look in a, well, if you look at this f of z, if you look at this x of z, what do you see consistent in those transform expressions, in the numerator in particular? There's a z. Now, if we just, that's all I wanted. So now we have a z, and if we did a partial fraction expansion directly on capital F of z, we would not have z's in the numerator, would we? We're just looking for constant numbers when we do a partial fraction expansion. So the strategy for inverse z transforming, in order to get expressions that are consistent with our table, what we do is we actually divide that z out before we perform our partial fraction expansion. Meaning now, capital F of z over z, and this was our f of z that we were given. Now we look at f of z over z, that's just equal to 1 over this product of linear factors. This now becomes 1 over z minus 1/2, z minus 3/4. And this is now just some alpha 1, z minus 1/2, plus some alpha 2, z minus 3/4. And I'm assuming you all have the TI-89 or the Inspire, right? So that you can quickly do this to find, or you can just type in this command, expand, or you can do it. You can find alpha 1 just like you did it in the Laplace. You say alpha 1 is now going to equal, it's going to equal this 1 over z minus 1/2, z minus 3/4. I simply multiply by z minus 1/2, which gives me this z minus 3/4, and I evaluate that where that z minus 1/2 vanished, which is at 1/2. That gives me 1 over 1/2 minus 3/4, which is a quarter with a negative sign, right? I have 50 cents minus 75 cents. Pull out your money. All right, so now I have minus a quarter. I bet on the wrong team. Minus 4, right? Alpha 2 is similar, except now we've now multiplied through by the factor z minus 3/4. That leaves us with 1 over z minus 1/2. Now we can do that math. You don't have to go home and tell your mom you're 25 cents in the hole. Now you're 25 cents ahead, I think, right? 1 over 75 minus 50. 1 over 1/4. Now we're 4. What does that tell us? Now we know that f of z, we can put that z back in. We now know that we have minus 4z over z minus 1/2 plus 4z over z minus 3/4. And we can find those in the z transform tables. You better be able to find this and this, which leads you to little f of n is equal to minus 4, 1/2 to the n, and we know what those powers of n are from our region of convergence. We know this is a right-sided sequence, so the n's have to be non-negative. Plus 4, 3/4 to the n for n greater than or equal to 0. Is that clear? What if we did have a donut? What about, and you might want to bring a donut Monday, because we're going from 5:30 to who knows, right? For our review session starting at 7. And if you have to leave, what? We have a donut-shaped region of convergence. Let's look at an example. I'm just going to give you the answer, and then we'll see what that actually sort of corresponds to. Or we'll go the other way. We'll find the z transform. Now we're saying that f of n is equal to one side, let's call it f sub 1 of n, of 2, 3 to the n for negative values of n, and it's f sub 2 of n. What? Sorry. I wanted to build a different example. We've already kind of looked. So let me make this one. This is not to scale. That's at 3. And where is this other one? Man, I can't even read my own writing. All these lines there. Let me change colors. This will erase everything. I knew it. Let's say this is now at 3, and let's say this is at 1/2. We know that when the region of convergence is exterior to the pole, we have a causal sided sequence. When our pole is, or the region of convergence is interior to a pole, then we have a anti-causal sequence. Now we can find the transform by looking at this f of n that has two different pieces associated with it. F of n and we can do these separately. We now know that capital F of z is going to be capital F sub 1 of z plus capital F sub 2 of z. F sub 1 of z is the left-sided, or the anti-causal, or the 2 I can pull out. And this now becomes 3 over z to the n. And now if I don't change my indices and just write down the expression, what do I know that needs to equal? Do you remember? I'll do the hard part. It's 2 times something. What's that infinite sum produce? You remember from before? And you can always rederive this. Is that right? And now, when does that converge? Now 3 over z, since we're doing negative indices, we're now saying 3 over z to the negative powers. When it was positive powers, we needed it to be less than 1. Now, because we have, what did I just say? When it was positive powers, it was less than 1. Now that it's negative powers, it has to be greater than 1, doesn't it? So we now need, for the region of convergence, we need 3 over z to be bigger than 1, or, well, maybe I'll do it this way. If I now multiply through by the absolute value of z, z is inside 3, isn't it? Do you need to see where that came from? You can rederive that, can't you? That particular result. So now what does that tell me as far as this piece and its region of convergence? For capital F sub 1 of z, that has a pole at 3. And what's the region of convergence look like for that piece? That's what we needed for that transform to converge. We needed the region of convergence to be inside of 3. F sub 2 is now 4 times this sum from n equals 0 to infinity of 1/2 to the n, z to the minus n, and when does that converge? If I say this is now 1 over z to the n, that z can go and be downstairs with 2, and I have 1 over 2z to the n. My indices are positive, so that 1 over 2z needs to be less than 1. Or z now needs to be bigger than 1/2. And this ends up being if we evaluate that infinite sum, 4 times z over z minus 1/2, with z exterior to 1/2. which we now have this pole at 1/2. But we need that region of convergence to be true for both poles, don't we? And a pole cannot be interior to, or lie inside the region of convergence. So we have to take the intersection of these two regions of convergence. We know what the region of convergence was for f sub 2. We know what it was for f sub 1. The region of convergence for f sub z is actually equal to the region of convergence for number 1, which was inside 3. Region number 2 was outside 1/2. And now we have that for our region of convergence. Is that time domain sequence f of n stable? What was f of n? You could just evaluate that and see, right? I have 2 times 3 to the n. What's that doing as a function of time for negative n? Now it's decaying, isn't it? On the left side for negative n. What's this f sub 2 of n doing on the right side? It's 1/2 raised to higher and higher powers. That's decaying. So now we have this and this. It's stable, isn't it? Where's our unit circle relative to this region of stability? Region of convergence. It's contained within the region of convergence, isn't it? So that says that f of n, our time domain sequence or waveform, even though it's two-sided, is bounded. It's stable. Is f sub n stable? Yes. Even though f sub n was two-sided. Questions on that? Yes.
So what does the pole outside of the unit circle?
What does the pole outside of the unit circle mean here is the question. You tell me. What does it mean? So now the pole outside the unit circle, it depends on what that pole, because that gives us this 3 to the n factor in our expansion or in our time domain waveform. It depends on what little n is that's raising that 3 to a power, doesn't it? Meaning, depending on the region of convergence, that 3 could correspond to a stable response or an unstable response. In this case, 3 is, or maybe I don't know if I'm going to be very consistent with what I say is where, but let's say the region of convergence is interior to 3. Something interior to a pole says what about that sidedness of that time domain mode? 3 to the n, what do we know about the little n? it's negative, isn't it? So now we have 3 to the minus 1, 3 to the minus 2, or we just say 1 over 3 to the first power, 1 over 3 squared. Oh, that's going to behave. Is that okay? Now, if I change the region of convergence, and I said, oh, these two poles, what happened to the other pole? Suppose these two poles were both interior to my region of convergence. So now I'm saying, suppose, I'm hoping I'm sort of converging on an answer. I'm kind of playing sides. You didn't know electrical engineering could be so punchline filled, huh? Full of punchlines. Where was I? Region of convergence. Take this to Leno, huh? No wonder he's tomorrow, isn't it? It's his last. I don't know, I don't watch him anymore. Okay, those are circles, but now suppose this. You could answer this a couple of different ways to get to the same answer. What do we know about 1/2 to the n and 3 to the n? If I said, what's the structure of your solution? You would say, oh, let's say that that's some W of n. I know that it's alpha 1, 1/2 to the n plus alpha 2, 3 to the n. For what values of n? Can you tell me for what values of n based on the region of convergence and these poles where they're located? They're positive, aren't they? They're non-negative values of n. So this expression is true for n greater than or equal to 0, right? Just based on the region of convergence. I haven't found my alpha 1 and alpha 2. Those aren't the same as in the last example. So they're not the same. It's alpha 1 bar and alpha 2 bar. It's something. And we know that we can directly add those because they're both on the same side of the region of convergence, right? There's no donut. So we don't have to worry about splitting this expression into a negative part and a positive part in terms of the time index. We know that the region of convergence contains a huge z, and because it contains a huge z, we know the negative time indices have to vanish. That's why we can say this. Can you tell me now about the stability of W of n? It's unbounded, isn't it? In this case. In the last case, it was well behaved, wasn't it? What's the difference? My unit circle is contained within the region of convergence. Where's my unit circle here? You can pretty yours up. It's not a part of the region of convergence, is it? So the region of convergence does not include or contain the unit circle. So that waveform is actually going to be unbounded in the time domain. But it does have a z-transform.
So does that mean that you can't just look at the poles anymore and say what the value?
That's correct. You can't just, the question is, you can't just look at the poles of this transfer function and claim stability or not, unless somebody prefaces your discussion and says, we're always going to work with causal waveforms. If they tell you that, then you know that all of these poles are always interior to, or the region of convergence is exterior to the poles. If they give you that additional piece of information, if they say all of your waveforms are causal, they're giving you a big hint. Then you can inverse Z transform without knowing explicitly what the region of convergence is. They just told it to you. They hinted it to you. It's a causal sequence. Okay, I know. Means it's unbounded in extent, the region of convergence. That means all the poles are lying inside the inside the region of convergence. Then stability can be determined by where the poles are. And if they gave you the other case, you could also determine based on where your poles are. Yes?
For the homework, I don't know if it's that time.
Which homework? Homework number 2. I guess we only have 2. I could have taken out my coin and flipped it, huh? But you know we can't flip coins on time anymore. Broadway Joe gets too excited and he flips it before he's supposed to. If you didn't get that, don't worry about it. Where was I? Oh, on this. You can, I don't think it really matters other than, well, yes, go ahead and assume these are causal. So now play as if you want your poles to be inside the unit circle for stability. Is that making sense? Now that I've confused you completely? But if you now have poles inside the unit circle, we'll sort of usually assume that we're working with causal time domain waveforms. In real life, it depends on what you're doing. So the question was, in real life, are we supposed to assume everything is causal? If we were dealing with dynamical systems, probably yes. But if we were talking about images or something else, then negative or anti-causal doesn't really matter. We might be looking at anti-causal behavior. That might be fine. We'll pick up at this place somewhere, one side or the other, on Monday.